Hello everybody, welcome to this new class of the Rule Governance course. In this week we are going to give an overview on several topics. We will talk of modeling of systems, of social systems, of agency, of how agency deals with institutions, concluding with a series of high-level insights about agility in organizations. Why do we model? There are several reasons. The most evident is that modeling can guide exploration. For instance, if we build a physical model of a bridge or of a ship, we can navigate a target object by means of this surrogate object. For this navigation to be meaningful, the model should maintain relevant characteristics of the target object. In this case, modeling can help us to figure out what questions to ask. It can bring to the foreground key design decisions, even uncover problems. A second reason why we model is to reify our understanding, that is, to select and write down what we believe it is relevant for the target domain. Consider, for instance, conceptual models as those specified by ontologies or some informal means. A third reason, consequent to the first, is that modeling can be used to check our understanding. We can reason with and about a model and reflect on the consequences it predicts. We check those predictions with our expectations. In case of dynamic processes, we can use the model to make animations that help us to visualize and then validate behavior by simulation. A fourth reason, consequent to the second, is that modeling helps in communication. Because abstractions are written with the right focus and neglect unnecessary details, communications become less redundant, less prone to errors, and thus more effective. A fifth reason is that modeling can be used not only to describe the world or a theory of the world that we have constructed, but we can use it also as a prescription to be used to guide the actualization of the object in an actual object. For instance, blueprints reveal the architecture of the target objects, whereas recipes instruct on the steps to follow to make a certain dish. Several types of model specification exist. They can be deterministic as a mathematical function or a map, or probabilistic, as for instance distributions issued from a set of samples. Models can be behavioral or procedural, that is, about a temporal sequence of events or actions. They can also be intentional, that is, models constructed by mentalization, looking at the model entity as it is provided with beliefs, with desires, and with intentions. Models can be formal and informal. Examples of formal models are business processes specifications, knowledge models, accounting models, as well as statistical models. Examples of informal models are all experts' conceptualizations and knowledge which may in part be verbalized. Those include prototypical cases, failure modes, best and bad practices, knowledge of specific requirements to be satisfied, as well as various heuristics used to take decisions, cautiously or not. In some cases, such knowledge or heuristics may be not shared as deemed generally unacceptable. Where modeling is applied. It is a general standard view to see at organizations as provided with three simultaneous views: business drivers or policy, planning or design, and operations, extra-functional, functional, and non-functional levels. We use models across all these to capture enterprise architectures, functional architectures, and technical architectures, to write down business requirements, functional requirements, and non-functional requirements. The first are meant to answer to why the organization is performing certain activities and include specifications about values supposedly promoted by those activities, as well as policies adopted by the organization. The second are meant to capture what an organization is doing, describing the functional goals its activities are making concrete. The third are meant to describe characteristics of the implementations, that is, how the organization is actually doing its activities. Now, let us focus more in general on what models are about. In practice, models are always about systems. A system is a set of interacting or interdependent components forming an integrated whole. Well-known examples of systems are operating systems, organisms as human bodies, but also theoretical systems as a certain branch of mathematics or a conceptual paradigm, and organizations. Two types of conceptualization of systems can be recognized: system as a totality or system as an assemblage or aggregate. Totalities are based on an organicistic metaphor. Components are defined by relations of interiority, that is, what the component is with respect to the whole. Those connections are necessary. In general, we cannot replace one component with another functionally equivalent. In other terms, totalities design worlds of necessity. In contrast, assemblages are based upon the metaphor of symbiosis. Components are primarily defined by how they interact with the other components. Those connections are obligatory for the interaction to be successful, but they are not necessary. A hermit crab can replace a sea anemone with another one functionally equivalent. The symbiosis will still be functioning. For these reasons, assemblage define worlds of possibility. Now, let us consider a very simple assemblage. We take a simple grain of sand. The structure of this grain is formed by a certain shape, and it is subjected to some physical laws, as for instance gravity. Let us imagine that I drop a lot of grains of sand from the same fixed position. After a while, I will see a pile forming up, which is the assemblage I want to investigate. The pile of sand is a whole, composed by interacting grains. Because of gravity, the grains below take upon the weight of the grains above. The macro characteristics of the pile are a consequence of the micro characteristics of the grains, but it is not trivial to infer them by looking only at the individual element. For instance, we can observe that while continuing dropping sand, the pile will exhibit superficial landslides. Those landslides occur in critical points, that is, when the system attempts to go beyond the maximum thresholds of the existing structure. Even if very simple, the sand pile shows us two fundamental requirements for aggregation. The organization from individuals to a collective entity requires some coordination capacity, in this case the piling up of the grain of sands. The maintenance of the collective entity requires some type of reparation capacity. For instance, the landslides, although they destroy part of the previous structure, result generally in more robust structures, able to sustain higher loads. The first characteristic of complex adaptive system is aggregate behavior. A collective behavior emerges from the interactions of the parts. The second characteristic is evolution. There is some selection, and in general the parts improve their ability to survive in their interaction with the surrounding parts. The third characteristic is adaptation. The parts develop rules to anticipate the consequences to certain signals given by the context. This is what we have observed with Pavlov's studies, but also, for instance, for all kinds of hoarding behavior, anticipating oil, water, or other types of shortages. Now, if we look at the sand pile, this is not a complex adaptive system because it does not manifest any anticipation. Plants, animals, humans, organization, ecological systems, socioeconomic systems, they are instead all complex adaptive systems. Now, if we need to describe complex adaptive systems, we need to model anticipation, or more in general, teleological types of behavior that can be projective, purposive, and etc. etc. How do we do that? We will now have a look on the stances that we take when we look at the world. We can look at the world by taking a physical stance, that is, interpreting it using the laws of physics. But we can look at the world also in terms of what we expect it to do. For instance, because we know it has been designed to do so. We don't interpret clocks by looking at the internal components, we just use them. However, the design stance is not always correct, because artifacts can break. When they break, we typically need to take a physical stance to see which internal components failed. On top of the design stance, we find the intentional stance, which is the stance that we take when we interpret an entity as an agent, ascribing it beliefs, desires, intents, and some rationality, adequate to do what the agent ought to do given its beliefs and desires. In this case, our abstraction is even higher than the design stance. If things do not work as we expected, it may be not only because the rationality of our reference did not work as expected, but also because we ascribed wrong belief, desires, or intentions. Note that we apply intentional stances not only to people, but also to fictional characters, as well as to animals. We then close this part of the lecture adding another stance beyond the three considered in Daniel Dennett's account. Similar, but yet different from the intentional stance, we find the institutional stance, that is, the stance of creating expectation upon a certain entity by ascribing powers, duties, and prohibitions derived from its membership to a social system with certain norms. The institutional stance, in a way, is in between a design stance, someone has written explicitly what we should expect, and an intentional stance. It concerns what individuals should know and should commit to in a certain context. As you may imagine, the normative frames we have presented in the previous class are part of the concept used to take an institutional stance.